What if a spacecraft, hurtling through the vast emptiness of space on a mission to Jupiter, suddenly locked its gaze on something no one expected? Something so unusual that the image it captured defies everything we thought we knew about comets. This isn't a glitch. It isn't a trick of light or a processing error. It's 3I Atlas, an interstellar traveller slipping silently through our solar system. Caught in a moment of cosmic mystery by Europe's Juice spacecraft. And what Juice has revealed in that fleeting snapshot could upend decades of comet science. Let me be clear about something right from the start. Comets have tails. We know this. We've studied them for centuries. But what Juice captured isn't what you'd expect from a routine observation. This image shows two distinct tails, visible with remarkable clarity, extending from a single nucleus like twin streams of light frozen in time. One tail pointing in one direction, another pointing somewhere else entirely. And here's what makes this moment so significant. Juice wasn't even designed to study comets. It's a Jupiter mission, built to explore the icy moons of the solar system's largest planet. Yet in November, it turned its instruments toward this interstellar object and captured something that has scientists around the world leaning forward in their chairs. Stay with me for the next few minutes, because what I'm about to walk you through isn't just about a comet with two tails. In this video, we're going to examine why Europe's most sophisticated spacecraft diverted from its primary mission to track this object, what those two tails actually tell us about 3I Atlas, why the full science data won't reach Earth until February 2026, and what this observation reveals about the unprecedented network of instruments now watching this interstellar visitor as it races toward its closest approach to Earth later this month. Now, before we go any further, I need you to do something for me. If you're as fascinated by these cosmic mysteries as I am, hit that like button right now. Drop a comment telling me where you're watching from, because I want to know how global this community really is. Are you watching from North America, Europe, Asia, Australia, somewhere else entirely? Let me know, because we're all witnesses to the same unfolding mystery, separated by distance but connected by curiosity. And if you haven't subscribed yet, do it now, because 3I Atlas is approaching Earth, and the coming weeks are going to bring us information that could reshape our understanding of interstellar objects. You don't want to miss what's coming. Here's what we know so far. On December 4th, ESA released an image taken by the navigation camera aboard the Juice spacecraft. The image shows 3I Atlas with two clearly visible tails extending from its nucleus. This isn't speculation. This isn't artistic interpretation. This is raw observational data captured by one of the most advanced spacecraft humanity has ever built. The image is striking in its simplicity. Against the darkness of space, you can see the comet's glowing nucleus and those two tails stretching outward like cosmic ribbons. One tail appears brighter, more defined. The other is slightly fainter but unmistakably present. But let's pause here for a moment, because I need you to understand why this matters. Comets are supposed to have tails. That's not news. When a comet gets close to the Sun, the solar radiation heats its icy surface, causing material to vaporize and stream away from the nucleus. This creates a tail, sometimes two tails actually. One tail is made of ionized gas, pushed directly away from the Sun by solar wind. The other is made of dust particles, following a slightly different path due to the pressure of sunlight. So technically, yes, comets can have two tails. This is established science. So why am I making such a big deal about this image? Because of the clarity, because of the distance, because of the context. Juice captured this observation from tens of millions of miles away from 3I Atlas. Think about that. This isn't a close-up flyby. This isn't Hubble staring at an object for hours to gather enough light. This is a navigation camera on a spacecraft designed for an entirely different mission, capturing an image clear enough to distinguish two separate tail structures. That tells us something about 3I Atlas itself. It tells us this object is active, bright, and producing enough material to create visible tails from enormous distances. And then there's the question that keeps circling back in my mind. Why was Juice looking at it in the first place? This spacecraft left Earth with one purpose: to reach Jupiter, to study Europa, Ganymede, and Callisto, to unlock the secrets of icy moons that might harbour conditions for life beneath their frozen surfaces. Jupiter is the destination. Jupiter is the mission. So what made ESA decide to turn Juice's instruments toward an interstellar comet? The official explanation is scientific opportunity. 3i Atlas is only the second confirmed interstellar comet ever detected. The first was 2i Borisov, discovered in 2019. These objects are extraordinarily rare. They originate from other star systems, travel through interstellar space for millions or billions of years, and occasionally pass through our solar neighborhood. When they do, scientists have a limited window to study them before they disappear back into the cosmic ocean. So, when 3i Atlas was discovered earlier this year, space agencies around the world took notice. Juice was already in space, already equipped with powerful instruments, and positioned in a way that made observation possible. It would have been wasteful not to take advantage of that opportunity. That explanation makes sense, it's logical, it's reasonable, but it doesn't fully explain the scale of what happened. Because Juice didn't just take a quick snapshot with its navigation camera, it deployed 5 separate scientific instruments to study 3i Atlas during its November encounter. 5, let me list them for you. Janus, the optical camera system. Magis, the infrared spectrometer. UVS, the ultraviolet spectrograph. SBY, the radio wave instrument. And PEP, the particle detector. Each of these instruments is designed to capture different aspects of the electromagnetic spectrum and the surrounding environment. Each one provides a unique layer of data, and ESA activated all of them. That's not a casual observation. That's a coordinated scientific campaign. That's a decision made at the highest levels of mission planning, weighing the cost of diverting resources against the value of the data that might be collected. And they decided it was worth it. They decided that whatever 3i Atlas might reveal was important enough to justify using a Jupiter mission to study it. So we come back to the image. 2 tails, clear separation, captured from millions of miles away, and behind that image 5 instruments collecting data that we won't see for another year and a half. That's the piece of this puzzle that keeps me awake at night. We're looking at one navigation camera photo, one single image released to the public. But there's a mountain of science data sitting in Juice's memory banks, data that won't be transmitted to Earth until February 2026. What's in that data? What did those 5 instruments see that we haven't been told about yet? ESA has given us a technical explanation for the delay. Juice is currently using its high-gain antenna as a heat shield to protect its instruments from solar radiation. That antenna is the primary communication link back to Earth. As long as it's oriented for thermal protection, the spacecraft can only transmit small amounts of data using its low-gain antennas. The full science dataset from the November observation is too large to send through that limited connection, so it sits on board, waiting, until Juice can reorient and use its high-gain antenna again. That won't happen until early 2026. I want to be clear about something. This explanation is technically sound, it makes sense, there's no reason to doubt it. But it creates a situation where we're staring at one image, knowing that there's vastly more information locked away in a spacecraft millions of miles from Earth, information we won't access for months. And in that gap between what we can see and what we're waiting to see, questions multiply. What did the infrared spectrometer detect about the comet's composition? What did the ultraviolet instrument reveal about the ionized gas in the plasma tail? What did the particle detector measure in the surrounding space? These aren't idle questions. They're the foundation of scientific understanding, and right now we're operating with incomplete information, which means we're left to wonder, we're left to speculate, we're left to examine this one image and ask ourselves what it's really showing us. Because even though we know comets can have 2 tails, even though we understand the physics behind them, there's something about this observation that feels significant in a way I can't fully articulate yet. Maybe it's the timing. Maybe it's the unprecedented network of observatories now tracking this object. Maybe it's the fact that we're watching an interstellar visitor pass through our solar system in real time, with more advanced instruments than we've ever had before. Whatever it is, it's pulling us forward into the rest of this investigation, because there's so much more to unpack here, starting with the mission itself and why Juice's presence in this part of space at this moment in time created such a unique opportunity to study something that doesn't belong to our sun. Let's talk about what Juice actually is, because understanding the spacecraft makes the 3i Atlas observation even more remarkable. Juice stands for Jupiter Icy Moons Explorer, and it's one of the most ambitious deep space missions the European Space Agency has ever attempted. Launched in April 2023, this spacecraft is designed to spend years travelling to Jupiter and then conducting detailed studies of 3 of its largest moons, Ganymede, Callisto, and Europa. These aren't just random rocks orbiting a gas giant. They're worlds in their own right, each believed to harbour vast oceans of liquid water beneath their icy surfaces. If life exists anywhere else in our solar system, these moons are prime candidates. Juice is massive by spacecraft standards. It carries 11 scientific instruments, from cameras and spectrometers to radar systems and magnetometers. It has solar panels that stretch wider than a basketball court when fully deployed. It's built to survive the intense radiation environment around Jupiter, which would fry most electronics in minutes. Everything about this mission is long-term, large-scale, and focused on a single destination. Jupiter, not comets, not asteroids, not interstellar visitors passing through, Jupiter and its moons. So when I tell you that Juice diverted to observe 3I Atlas in November, I need you to understand what that means operationally. Space missions don't just change course on a whim. Every maneuver is planned months in advance. Every instrument activation is scheduled. Every second of spacecraft time is accounted for because deep space missions operate under tight constraints. Power is limited. Communication windows are limited. Data storage is limited. You don't waste any of these resources unless there's a compelling reason. And yet, ESA made the decision to point Juice at an interstellar comet. They planned the observation sequence. They coordinated the instrument activations. They allocated the power and data storage necessary to capture what they were seeing. This wasn't a last-minute improvisation. This was a deliberate choice made by mission planners who looked at the trajectory of 3I Atlas, looked at Juice's position in space, and decided the scientific value justified the diversion. Now, let's be precise about what happened. In early November, Juice was already millions of miles from Earth on its long journey toward Jupiter. It had completed a flyby of the Moon and Earth as part of a gravity assist maneuver designed to accelerate it toward the outer solar system. During this phase of the mission, the spacecraft was in a unique position. It was relatively close to the Sun compared to where it will be when it reaches Jupiter. It had a clear line of sight to 3I Atlas. And most importantly, the comet was at a point in its orbit where it was bright enough and active enough to study with Juice's instruments. The observation campaign began in late October, with initial tracking and continued through early November. The closest approach between Juice and 3I Atlas occurred on November 4th, though the spacecraft was still millions of miles away from the comet. During this period, Juice's instruments were turned toward the comet, capturing data across multiple wavelengths. The navigation camera took the image we're now looking at. The science instruments collected their data sets, and then the spacecraft continued on its primary mission, leaving 3I Atlas behind. But here's where it gets interesting. Juice wasn't the only spacecraft watching. Around the same time, NASA's Psyche spacecraft, which is on its way to study a metal-rich asteroid, also observed 3I Atlas. So did the Hubble Space Telescope. So did ground-based observatories around the world. This wasn't one isolated observation by a single mission. This was a coordinated effort involving multiple space agencies, multiple instruments, and multiple observation strategies. Everyone was looking at the same object at roughly the same time. Why? Because opportunities like this don't come around often. Interstellar objects are rare. The first one, 1I Oumuamua, was discovered in 2017, and by the time scientists realized what it was already too far away to study in detail. The shape, the trajectory, the strange acceleration it exhibited, all of it sparked debates that continue to this day. We simply didn't get enough data. When 2I Borisov was discovered in 2019, astronomers were better prepared. They tracked it for months, gathering spectroscopic data, analysing its composition, comparing it to comets from our solar system. It was the first interstellar comet we could actually study. And now we have 3I Atlas, the third confirmed interstellar object. But this time, we have even more advanced tools available. We have spacecraft already in position. We have telescopes that weren't operational during the Borisov observations. We have better tracking software, better communication networks, better international coordination. In short, we have the ability to study this object with unprecedented detail. And space agencies around the world decided to use that capability. So when ESA turned Juice toward 3I Atlas, they weren't acting alone. They were part of a larger scientific community seizing a rare opportunity. And the fact that they committed so many of Juice's resources to this observation suggests they believed the data would be worth it. They believed that whatever this comet might reveal about interstellar objects, about cometary behaviour, about the composition of material from other star systems would justify the cost. But there's another layer to consider. Juice is a mission designed to study icy bodies. Europa, Ganymede, Chand and Callisto are covered in ice. They have subsurface oceans. They experience interactions with Jupiter's magnetic field and radiation. The instruments aboard Juice are specifically built to study these kinds of environments. So when you point those same instruments at an icy comet, you're using tools perfectly suited for the job. The spectrometers can analyze the comet's composition. The particle detectors can measure the solar wind interactions. The cameras can capture the structure of the tails and the coma. In a sense, observing 3i Atlas was a natural extension of what Juice was designed to do. Still, the question lingers. Why this much attention? Why coordinate observations across multiple missions? Why deploy all 5 science instruments instead of just taking a quick photo? I think the answer lies in what 3i Atlas represents. It's not just a comet, it's a piece of another star system. It formed around a different sun, in a different part of the galaxy, under conditions we can only guess at. By studying it, we're not just learning about comets in general. We're learning about the diversity of planetary systems beyond our own. We're learning what kinds of materials exist out there in the interstellar medium. We're learning how common these objects might be and what they can tell us about the history of our galaxy. That's the kind of science that justifies a mission diversion. That's the kind of opportunity you don't pass up. And so Juice, a spacecraft built to explore Jupiter's moons, became part of the observational campaign tracking an interstellar visitor through our solar system. It captured an image showing 2 distinct tails. It collected data with 5 separate instruments, and now we wait, knowing that the full picture won't emerge until early 2026, when that data finally makes its way back to Earth. But before we get to the waiting game, before we dive into what those 2 tails actually mean and why the observation is so unusual, I need to walk you through the timeline of what happened. Because the sequence of events, the delays, the coordination between multiple agencies, all of it paints a picture that's more complex than it first appears, and that's where we're headed next. Now we need to talk about what you're actually looking at when you see that image of 3i Atlas with 2 tails stretching across the frame. Because while the phenomenon might seem straightforward, the reality is layered with physics, dynamics, and details that reveal just how active and complex this interstellar visitor truly is. And understanding those details is the key to understanding why this observation matters so much. Let's start with the basics. Comets are often called dirty snowballs, a term that undersells their complexity but captures the essential idea. They're made of ice, rock, dust, and frozen gases, material left over from the formation of a planetary system. When a comet is far from the Sun, it's essentially inert, a cold chunk of ancient material drifting through space. But as it gets closer to the Sun, something dramatic happens. Solar radiation begins to heat the surface. The ice starts to sublimate, turning directly from solid to gas without passing through a liquid phase. This releases dust particles that were trapped in the ice, and suddenly, you have a comet that's actively shedding material. This material forms a glowing cloud around the nucleus called the coma, and from the coma, tails begin to extend. Not 1 tail, but 2. This is where most people's understanding of comets breaks down, because we tend to think of a comet tail as a single feature, like the tail of a kite streaming behind it. But comets are more complex than that. They have 2 types of tails, and those tails behave very differently. The first tail is the plasma tail, sometimes called the ion tail. This is made of ionized gas, molecules that have been stripped of their electrons by solar radiation. These charged particles interact with the solar wind, the constant stream of charged particles flowing outward from the Sun. The solar wind pushes the plasma tail directly away from the Sun, no matter which direction the comet is travelling. If you could watch a comet orbit the Sun, you'd see its plasma tail always pointing away from the Sun like a compass needle. This tail is usually blue or bluish-white in images because of the specific wavelengths of light emitted by ionized molecules. The second tail is the dust tail. This one is made of solid particles, tiny grains of rock and dust, released when the comet's ice sublimates. These particles aren't charged, so they don't interact with the solar wind the same way ionized gas does. Instead, they're pushed away from the comet by the pressure of sunlight itself. Yes, light has pressure. It's incredibly faint, but over time and distance, it's enough to push small particles along curved paths. The dust tail tends to be yellowish or white in images. reflecting sunlight like any other solid material. And because these particles follow slightly different trajectories depending on when they were released and how large they are, the dust tail often appears broader and more curved than the plasma tail. So in theory, every active comet should have two tails, one pointing directly away from the sun, made of ionized gas, one following a curved path made of dust. But here's the thing, most of the time we don't see both tails clearly. They overlap, they blend together. The angle we're viewing from doesn't allow for clear separation, or the comet isn't active enough to produce prominent tails in both categories. It takes specific conditions for both tails to be visible and distinct in the same observation. And that's exactly what Juice captured when it looked at 3I Atlas. Two tails, clearly separated, extending in different directions from the nucleus, one brighter and more defined, likely the plasma tail, the other slightly fainter, probably the dust tail. The geometry of the observation, the angle between Juice, the comet and the sun, all aligned in a way that allowed this dual structure to be visible. And that's rare. It's not impossible. It's not unprecedented. But it's rare enough that when you capture it from millions of miles away with a navigation camera, it's worth paying attention. But let's dig deeper, because the existence of two tails isn't the only thing that makes this observation significant. It's the clarity. It's the fact that Juice could resolve these structures from such a distance. Think about what that means. Light from the sun hits 3I Atlas. Some of that light is reflected by dust particles in the tails. Some of it is emitted by ionized gas molecules. That light travels across millions of miles of space to reach Juice's camera. The camera captures it, and the resulting image is clear enough that you can distinguish two separate tails. That tells you the comet is producing a lot of material. It tells you the tails are bright, extensive, well-formed. It tells you 3I Atlas is an active, dynamic object, not a quiet, inert rock. And here's where it gets even more interesting. Juice didn't just take a photo with its navigation camera. Remember, 5 science instruments were pointed at this comet. Let's talk about what each of those instruments might have detected, because even though we won't see the data until 2026, we can make some educated guesses based on how these instruments work. Janus, the optical camera system, would have captured high-resolution images in visible light. These images would show the structure of the nucleus, the extent of the coma, the morphology of the tails. They'd provide visual detail that goes far beyond what the navigation camera can capture. Scientists will use these images to measure the size of the nucleus, estimate the rate at which material is being expelled, and track changes over time if multiple images were taken. Magis, the infrared spectrometer, would have analysed the composition of the comet's material. Different molecules emit and absorb infrared light at specific wavelengths. By measuring those wavelengths, scientists can identify what the comet is made of: water ice, carbon dioxide, methane, ammonia. Complex organic molecules, Magis can detect all of these, and because 3I Atlas is an interstellar object, comparing its composition to comets from our solar system could reveal whether interstellar material is fundamentally different or surprisingly similar. UVS, the ultraviolet spectrograph, would have focused on the ionized gas in the plasma tail. Ultraviolet light is emitted by excited atoms and molecules, particularly those that have been ionized by solar radiation. UVS can measure the density of these particles, their distribution, and how they interact with the solar wind. This data is crucial for understanding the comet's activity level and how much material it's losing as it moves closer to the sun. SDUI, the radio wave instrument, would have studied the comet's interaction with the solar wind from a different angle. Radio waves can penetrate regions of space that visible light can't, providing information about the magnetic fields and plasma environment around the comet. This is particularly useful for understanding how the solar wind shapes the plasma tail and whether there are any unexpected interactions happening. And finally, PEP, the particle detector, would have measured the charged particles in the space around 3I Atlas. As the solar wind interacts with the comet's coma and tails, it creates complex particle dynamics. Some particles are accelerated, some are deflected. PEP can measure these effects directly, providing ground truth data that complements the remote sensing observations from the other instruments. 5 instruments, 5 different perspectives on the same object, 5 layers of data that, when combined, will give scientists the most comprehensive view of an interstellar comet we've ever had. And all of that data is currently stored in Juice's memory, waiting to be transmitted back to Earth. We have one navigation camera image, one glimpse of what Juice saw, but the full picture is still locked away. So when you look at that image of 3i Atlas with its two tails, you're not just seeing a comet, you're seeing the visible tip of an enormous dataset. You're seeing the preview of a scientific investigation that won't be complete for another year and a half, and that waiting period, that gap between observation and understanding, is where speculation grows. It's where questions multiply. It's where people start to wonder whether the official explanations tell the whole story. Now, I want to be careful here. There's no evidence of any cover-up or hidden agenda. The technical explanation for the data delay makes sense. But human nature being what it is, when you tell people they have to wait months to see the full results of an observation, they start to ask why. They start to wonder what's being withheld. They start to connect dots that may or may not be there. And in the case of 3i Atlas, there are a lot of dots to connect, starting with the distance from which this image was captured, and what that distance implies about the object itself. Distance in space is difficult for the human mind to truly grasp. We're used to thinking in terms of miles or kilometers on Earth, distances we can drive or fly. But space operates on a scale so vast that our usual reference points become meaningless. When I tell you that Juice was millions of miles away from 3i Atlas when it captured that image, the number itself doesn't convey the reality of what that means. So let me try to give you some context that makes the achievement more tangible. Consider this. The Moon is about 250,000 miles from Earth. When astronauts traveled to the Moon during the Apollo missions, they crossed the largest distance any human has ever travelled from home. That journey took several days. The Moon looks large in our night sky because cosmically speaking it's right next door. But even at that distance, details on the lunar surface are difficult to see without a telescope. You can make out the broad features, the Maria and the Highlands, but you can't see individual craters or rocks or anything smaller than large regional features. Now multiply that distance several times over. That's roughly where Juice was in relation to 3i Atlas during the November observation. The spacecraft and the comet were separated by a gulf of space so large that light, travelling at over 180,000 miles per second, took noticeable time to cross it. And yet, from that distance, Juice's navigation camera captured an image clear enough to distinguish two separate tails. That's remarkable. That's a testament to both the quality of the spacecraft's instruments and the brightness of the comet itself. Let's think about what that brightness implies. For 3i Atlas to be visible and resolvable from such a distance, it has to be reflecting or emitting a significant amount of light. The nucleus itself is relatively small, probably no more than a few miles across. But the coma, the cloud of gas and dust surrounding the nucleus, can extend for tens of thousands of miles, and the tails can stretch for millions of miles. All of that material is scattering sunlight, reflecting it in all directions. Some of that reflected light reached Juice's camera, and there was enough of it to create a clear image. This tells us something important about 3i Atlas's activity level. It's not a quiet, inactive comet. It's actively outgassing. It's shedding material. It's responding to solar heating in a way that produces visible, extensive tails. And remember, when Juice made this observation, 3i Atlas was still relatively far from the Sun. It wasn't at its closest approach. It wasn't at peak activity. It was already bright enough to be studied from millions of miles away. What happens as it gets closer to the Sun? What happens when solar heating intensifies and the comet becomes even more active? That's a question scientists are eager to answer, and it's why observations are continuing. Ground-based telescopes are tracking 3i Atlas as it moves through its orbit. Hubble has been watching it. Psyche captured its own data, and amateur astronomers with backyard telescopes are contributing observations to a growing database. Everyone wants to see how this object evolves as it approaches its closest point to the Sun, which will happen later this month. But let's return to the distance factor and what it means for the observation itself. When you're observing an object from millions of miles away, you're not just dealing with the challenge of distance, you're also dealing with geometry. The angle between your spacecraft, the object you're observing, and the Sun determines what you can see. If the angle isn't right, you might not see both tails clearly. You might only see one, or they might overlap in a way that makes them hard to distinguish. The fact that Juice captured both tails distinctly means the geometry was favourable. The spacecraft was positioned in just the right place at just the right time to see this dual structure, and that raises an interesting point. Was this positioning deliberate? Did mission planners calculate the optimal observation window based on where Juice would be and where 3i Atlas would be? Or was it fortunate timing? I suspect it was a bit of both. Orbital mechanics are predictable. You can calculate where every object in the solar system will be at any given time with extraordinary precision. If ESA knew they wanted to observe 3i Atlas, they could have planned the observation to coincide with a favourable geometry. But you can't control everything. You can't predict exactly how active the comet will be, or whether clouds or debris will interfere with the observation. Some element of luck is always involved. What we do know is that the observation succeeded. Juice was in the right place. The comet was bright enough. The geometry was favourable. And the result is an image that's generating conversation across the scientific community and beyond. But the image is only part of the story. Behind that single photo is a wealth of data captured by those 5 science instruments. Data that will take the clarity and detail to another level entirely. Think about it this way. The navigation camera is designed to help Juice orient itself in space. It's a functional tool, not a scientific instrument. It's not optimized for studying comets or capturing high-resolution images of distant objects. It's meant to provide situational awareness. The fact that it captured a usable image of 3i Atlas speaks to the comet's brightness. But the science instruments are a different story. They're designed specifically to extract information from the objects they observe. They're optimized for sensitivity, resolution, and precision. When Janus took images, it wasn't just snapping a photo. It was recording light intensity, tracking structure, measuring dimensions. When Magis analyzed the infrared spectrum, it wasn't just detecting heat. It was identifying molecular signatures, mapping composition, revealing chemical details invisible to the human eye. And all of that data is currently sitting in Juice's memory banks, millions of miles away, waiting for the spacecraft to reorient and transmit it back to Earth. That's the part that keeps me coming back to this story. We've seen one image, one snapshot from one camera. But there's a mountain of information we haven't seen yet. And until we do, we're left to wonder what it contains. What did those instruments reveal? What details about 3i Atlas are we still waiting to discover? The distance factor also has another implication. If Juice could see 3i Atlas this clearly from so far away, what could a spacecraft see if it got closer? What if a future mission deliberately targeted an interstellar object for a flyby? We've sent spacecraft to study comets before. We've flown through their tails, sampled their material, even landed on their surfaces. But those were comets from our own solar system. Imagine what we could learn from a close encounter with an interstellar visitor. The composition of material from another star system, the structure of its nucleus, the way it responds to our sun's radiation. It would be like studying a piece of the galaxy brought to our doorstep. That's the long-term vision. That's the future of interstellar object research. But for now, we're working with what we have. Distant observations from spacecraft that weren't designed for this purpose. Telescopes on Earth capturing what they can through the distortion of our atmosphere. And one very clear image from a Jupiter mission that happened to be in the right place at the right time. It's not a close encounter. It's not a dedicated study. But it's the best we've got, and it's already revealing more about 3i Atlas than we knew before. So as we move forward into the next part of this investigation, keep that distance in mind. Keep the scale of what's happening in perspective. We're watching an object from another star system pass through ours. We're doing it from millions of miles away. And we're still managing to gather data that will push our understanding forward. That's the power of modern space exploration. That's what happens when you combine advanced instruments, careful planning, and a willingness to seize opportunities when they present themselves. But the observation is only half the story. The other half is what happens to the data after it's collected, and that's where things get interesting, because the timeline between observation and revelation is longer than you might expect. Here's the part that frustrates people. Here's the part that generates questions and suspicion and endless speculation across forums and comment sections. Juice observed 3i Atlas in November. We're now in December. The image was released on December 4th. But the full science data from those 5 instruments won't be transmitted to Earth until February 2026. That's more than a year away. And in the age of instant information, in a world where we expect data to be available immediately, that kind of delay feels wrong. It feels deliberate. It feels like something is being withheld. So let me walk you through exactly why this delay exists. Because the technical explanation is actually quite fascinating, even if it's not as dramatic as some people might hope. It comes down to 3 factors: spacecraft orientation, antenna configuration, and data transmission rates. First, spacecraft orientation. Juice is currently on its way to Jupiter, which means it's travelling through the inner solar system where solar radiation is intense. The spacecraft's instruments are sensitive. They're designed to operate in the cold, radiation-heavy environment around Jupiter, not the relatively hotter conditions closer to the Sun. To protect these instruments, Juice uses its high-gain antenna as a heat shield. This antenna is large, dish-shaped, and positioned to block direct solar radiation from hitting the spacecraft's main body. It's an elegant solution that allows the spacecraft to survive the journey without adding extra thermal protection systems. But here's the catch. That high-gain antenna is also Juice's primary communication link with Earth. It's how the spacecraft transmits large amounts of data at relatively high speeds, and right now, it's pointed at the Sun, acting as a shield, which means it's not pointed at Earth. The spacecraft can still communicate using its low-gain antennas, which are omnidirectional and can send signals in multiple directions. But low-gain antennas have limited bandwidth. They're fine for basic telemetry, health checks, and small data packets. They're not suitable for transmitting gigabytes of science data. So the data sits on board, stored in Juice's solid-state memory, waiting for the spacecraft to reach a point in its journey where it can safely reorient without exposing its instruments to harmful solar radiation. That point will come in early 2026, when Juice is farther from the Sun and can use its high-gain antenna for communication without risking overheating. At that time, the spacecraft will begin transmitting the stored data back to Earth, and scientists will finally get to see what those 5 instruments captured during the November observation. Now, this explanation is technically sound. It's consistent with how spacecraft operations work. It's the kind of trade-off that mission planners make all the time. You can't do everything at once, you have to prioritize. In this case, protecting the spacecraft takes precedence over immediate data transmission. That makes sense. It's logical. It's reasonable, but it also creates a situation where we're left in the dark. We know Juice observed 3i Atlas. We know 5 instruments collected data. We've seen 1 navigation camera image. But that's all. The rest is locked away in a spacecraft millions of miles from Earth, and we have to wait more than a year to see it. And in that waiting period, questions emerge. What's in that data? What did those instruments detect? Is there something surprising, something unexpected, something that challenges our current understanding? We don't know. We can't know. Not until February 2026. And here's where human psychology enters the picture. When you tell people they have to wait to see information, especially information related to something unusual or rare, some of them will start to wonder why the wait is necessary. They'll question the official explanation. They'll look for alternative reasons why the data might be withheld. And in the case of space exploration, where there's always been an undercurrent of suspicion about what governments and space agencies are really doing, that questioning can spiral into speculation pretty quickly. Let me be absolutely clear about something. There's no evidence of any deliberate withholding of information. There's no indication that ESA is hiding something. The explanation they've provided about antenna orientation and data transmission limitations is consistent with standard spacecraft operations. This isn't a conspiracy, it's engineering. But the gap between observation and revelation creates space for doubt, and some people will fill that space with theories that go beyond the official narrative. I've seen the discussions online, people pointing out that a month passed between the observation and the release of the navigation camera image. People questioning why ESA chose to release that particular image on December 4th instead of immediately after the observation. People connecting this delay to other recent space announcements and suggesting some kind of coordinated information release schedule. Are these connections real, or are they just pattern recognition run wild, the human brain's tendency to see meaning in random events? Honestly, I think most of it is just the nature of how space missions work. Data takes time to process. Images need to be calibrated, corrected for instrumental effects, checked for errors. Scientists have to review what they've captured before releasing it to the public. And space agencies have communication schedules, press offices, coordination with other institutions. A month between observation and public release isn't unusual. It's actually pretty fast by the standards of deep space missions. But I also understand why people ask questions. We live in an era where information moves instantly. When something happens on Earth, we expect to see photos and videos within minutes. But space doesn't work that way. The distances are too vast. The communication links are too limited. The data processing requirements are too complex. there's an inherent delay built into the system, and that delay feels unnatural to people who are used to real-time updates, so we wait. We wait for February 2026, we wait for Juice to reorient, we wait for the high-gain antenna to start transmitting, we wait for the science data to cross millions of miles of space and arrive at receiving stations on Earth. We wait for scientists to process that data, analyze it, compare it to models and predictions and draw conclusions, and then, eventually, we'll get to see what those 5 instruments revealed about 3i Atlas. But here's the thing, the story doesn't end in February 2026. That's when we'll get the Juice data. But 3i Atlas is still out there, still moving, still being observed by other instruments. Hubble is watching it. Ground-based telescopes are tracking it. Amateur astronomers are capturing images. And as the comet approaches its closest point to the Sun later this month, all of those observations will provide new data, new insights, new pieces of the puzzle. The Juice observation is one snapshot in time, one moment in the comet's journey through our solar system. But the full story unfolds over weeks and months as multiple instruments contribute their perspectives. And that's actually one of the most exciting aspects of modern astronomy. We're not relying on a single observation from a single instrument. We're building a comprehensive picture from multiple sources. Each observatory, each telescope, each spacecraft adds a layer of information. And when you combine all of those layers, you get a view that's far richer and more detailed than any single observation could provide. That's the power of coordinated observation campaigns. That's why space agencies around the world are working together to study 3i Atlas. But the coordination itself raises questions, doesn't it? Why are so many resources being devoted to this one object? Yes, interstellar comets are rare. Yes, they're scientifically valuable. But the level of attention 3i Atlas is receiving goes beyond what you'd expect for a routine astronomical event. Multiple spacecraft, multiple telescopes, multiple space agencies coordinating their observations. That's a lot of effort for something that's supposedly just a comet passing through. Is there something about 3i Atlas that we're not being told? Is there a reason why it's attracting this much attention beyond its interstellar origin? Or is the scientific community simply being thorough, taking advantage of every available tool to study a rare opportunity? I think the answer is probably the latter, but I also think it's worth noting that the scale of the observation campaign is unusual. It suggests that scientists believe this object is particularly important, particularly valuable as a research target. And that makes the wait for the Juice data even more frustrating, because we know there's information sitting in that spacecraft that could help us understand why. So we're left in a holding pattern. One image released, full science data delayed until 2026, multiple observations underway by other instruments, and a growing sense that 3i Atlas is more significant than just another interstellar visitor. But significance requires context. It requires understanding the sequence of events, the timeline of observations, and how different pieces of data fit together. And that's what we need to examine next, because the timing of the Juice observation, the timing of the image release, and the timing of other related announcements create a pattern that's worth exploring, even if that pattern might not mean what some people think it means. Let's put together the timeline, because when you line up the dates and events, you start to see how this observation fits into a larger context of space exploration and scientific investigation. And while I'm not going to sit here and tell you there's some grand conspiracy at play, I do think the sequence of events is worth examining carefully, because it reveals how modern astronomy operates and how information flows from observation to public release. November 4th. That's when Juice made its closest approach to 3i Atlas. The spacecraft's instruments were trained on the comet, data was collected. The observation campaign that had begun in late October reached its peak. And then Juice continued on its trajectory toward Jupiter, leaving the comet behind. At this point, the data exists. It's stored in the spacecraft's memory. But nobody on Earth has seen it yet. There's been no transmission. There's been no preliminary analysis. The observation is complete, but the results are locked away. Now, you might expect that ESA would immediately start talking about this. You might expect press releases, announcements, some indication that a major observation had just occurred. But that's not how it works. Space agencies don't typically announce observations until they've had a chance to verify the data, process the images, and understand what they've captured. So November passes with no public mention of the Juice observation. People following the mission might have known it was planned, but the general public had no idea. Meanwhile, other things are happening in the space community. In mid-November, NASA releases new images from the Psyche spacecraft, which is on its way to study a metal-rich asteroid. Some of those images show 3i Atlas in the background of other observations. Hubble also releases data around this time showing the comet. Ground-based observatories are publishing their findings, so there's activity around 3i Atlas throughout November. Multiple sources are producing data, but the Juice observation remains unannounced. Then December arrives, December 4th, specifically. ESA releases the navigation camera image showing 3i Atlas with two distinct tails. The press release explains what Juice did, when it happened, and why the full science data won't be available until 2026. And suddenly, the observation that occurred a month earlier is front-page news in the astronomy community. People are sharing the image, articles are being written, discussions are happening across social media and forums. The Juice observation is now public knowledge. So why the delay between November 4th and December 4th? A month seems like a long time in the age of instant communication, and this is where some people start to see patterns that might not exist. They point out that December 4th is exactly 1 month after the closest approach. They note that other space agencies released their 3i Atlas data around the same time. They suggest that maybe there's coordination happening behind the scenes, some kind of scheduled information release that's being managed across multiple institutions. Is that true? Honestly, I doubt it. But I can see why people think it. When multiple space agencies release information about the same object within a similar time frame, it creates the appearance of coordination, and in some sense, there probably is coordination. Scientists at different institutions talk to each other, they share data, they publish papers together. There's definitely communication happening across agencies. But coordinated information release? A deliberate schedule to control when the public learns about things. That's a bigger claim, and it requires more evidence than just noting that announcements happened close together. The simpler explanation is that processing data takes time. When Juice captured that navigation camera image, it had to be transmitted to Earth. Remember, even though the full science data is delayed, navigation camera images are small enough to be sent via Logan antennas. So the image arrived on Earth sometime in November. Then it had to be processed. Raw images from spacecraft aren't ready for public consumption. They have to be calibrated, corrected for camera artifacts, oriented properly and checked for errors. All of that takes time. Meanwhile, scientists are reviewing the image. They're comparing it to their predictions. They're deciding what information to include in the press release. They're coordinating with ESA's communication office to determine the best time to announce the observation. And they're probably also coordinating with other institutions that are observing 3i Atlas to make sure their announcements don't conflict or overlap in confusing ways. That's not conspiracy. That's just good communication practice. So December 4th arrives, and ESA releases the image. The press release explains the observation, mentions the delayed science data, and provides context about why Juice was observing an interstellar comet in the first place. And the astronomy community responds. Articles appear in science news outlets. Space enthusiasts share the image. And people like me start digging into what it all means, what the image shows, and what questions remain unanswered. But here's what interests me about the timeline. Throughout November and early December, 3i Atlas was being observed by multiple instruments. Juice wasn't alone. Hubble was watching. Psyche captured data. Ground-based observatories were tracking the comet's progress. And all of these institutions were releasing their data on their own schedules, based on their own internal processes. Hubble's data might come out 1 week, Psyche's data another week. Ground-based observations are published as papers in scientific journals, which have their own review and publication timelines. There's no grand coordination. There's just a bunch of independent groups studying the same object and releasing their findings as they're ready. But when you're on the outside looking in, when you're trying to understand what's happening based on press releases and news articles, it can look like there's a pattern. It can look like information is being released in a controlled, deliberate way. And maybe, in a sense, it is. Not because there's a conspiracy, but because institutions have communication strategies. They want their announcements to get attention. They don't want to be drowned out by other news. So they pick times to release information that maximize visibility. That's just smart communication. Still, the month-long gap between observation and announcement is worth noting. It's not suspicious. It's not evidence of anything sinister. But it does highlight the fact that there's always a delay between when something happens in space and when we learn about it. and in that delay the information exists in a kind of limbo. It's been captured, it's stored somewhere, but it's not yet public. And for people who are eager to know what's been discovered, that delay can feel frustrating. What's even more frustrating is knowing that the navigation camera image is just the beginning. The real data, the science data from those 5 instruments, is still months away. We're looking at one photo and trying to extrapolate what the full dataset might contain. We're speculating based on incomplete information. And that's a recipe for both excitement and anxiety, because we know there's more to the story, but we have no idea what that more might be. And here's the other layer to consider. While we're waiting for the Juice data, 3i Atlas is still moving. It's getting closer to the Sun. It's becoming more active, and that means observations are ongoing. Every day, telescopes are pointed at this comet. Every day, new data is being collected. Some of that data is being released immediately. Amateur astronomers post their images online. Professional observatories publish their findings in preprint archives. So there's a constant stream of new information about 3i Atlas flowing into the public domain, even while the Juice data remains locked away. This creates a strange situation, where we're simultaneously learning more about the comet and waiting for information that's already been collected but not yet revealed. It's like watching a mystery unfold in real time while knowing that someone has the final chapter of the book but won't let you read it yet. And that tension, that gap between what we know and what we're waiting to know, is part of what makes this story so compelling. But the timeline also raises practical questions. What happens if something unexpected is discovered before the Juice data is released? What if ground-based observations reveal something about 3i Atlas that contradicts what the navigation camera image suggests? What if Hubble or another spacecraft detects anomalous behaviour? Does that change how we interpret the Juice observation? Does it add urgency to getting that science data transmitted back to Earth? These are the kinds of questions that scientists are probably asking themselves right now. They have preliminary data from Juice. They have observations from other sources. They're trying to build a coherent picture of what 3i Atlas is and how it's behaving. But they're doing it with incomplete information, waiting for the missing pieces to arrive. And in the meantime, the comet continues its journey through our solar system, indifferent to our attempts to understand it. So the November timeline isn't just about when things happened. It's about the flow of information, the gap between observation and revelation, and the way modern astronomy operates in an era of coordinated international research. It's about understanding that what we see in press releases is just the tip of the iceberg, that there's always more data being collected, more analysis being conducted, more questions being asked behind the scenes, and sometimes the most interesting part isn't what's been revealed, but what's still waiting to be discovered, which brings us to the instruments themselves and what they might tell us once that data finally arrives. 5 instruments. That's what ESA deployed to study 3i Atlas during Juice's November observation. 5 different tools, each designed to capture a specific aspect of the comet's structure, composition, and behaviour. And when you understand what each of these instruments does, you start to realise just how comprehensive this observation was. This wasn't a casual glance. This was a coordinated scientific investigation using some of the most sophisticated space-based instruments humanity has ever built. Let's start with Janus, the optical camera system. This is what most people think of when they imagine a spacecraft taking pictures. Janus is designed to capture high-resolution images in visible light, the same wavelengths our eyes can see, but unlike the navigation camera, which is meant for basic imaging, Janus is optimized for scientific observations. It has better resolution, better sensitivity, and better control over exposure settings. When Janus looked at 3i Atlas, it would have captured detailed images of the nucleus, the coma, and the tail structures. These images will allow scientists to measure the size of the nucleus, estimate how much material is being expelled, and track changes in the comet's activity over time if multiple images were taken. What makes Janus particularly valuable for studying comets is its ability to resolve fine details. The navigation camera gave us a clear view of the 2 tails, but Janus will show us the structure within those tails. Are they smooth and uniform, or are there clumps and streamers? Is the coma spherical, or does it have asymmetries that suggest uneven outgassing? These are the kinds of questions Janus can help answer. Next is Magis, the infrared spectrometer. This instrument operates in wavelengths beyond what human eyes can see in the infrared part of the spectrum. everything emits infrared radiation, and the specific wavelengths emitted or absorbed depend on the material's composition and temperature. Magis measures these wavelengths to identify what molecules are present in the comet. Water ice, carbon dioxide, methane, ammonia, complex organic molecules. Each of these has a unique infrared signature, and Magis can detect them. Why does composition matter? Because 3I Atlas is an interstellar object. It didn't form in our solar system. It came from somewhere else, around another star under different conditions. By analysing its composition, scientists can compare it to comets native to our solar system and look for differences or similarities. Are interstellar comets made of the same materials as our comets, suggesting that planetary formation is similar across the galaxy? Or are there significant differences hinting at diverse chemical environments around different stars? Magis will help answer these questions. Then there's UVS, the ultraviolet spectrograph. Ultraviolet light is emitted by ionized atoms and molecules, particularly those that have been energized by solar radiation. When the sun's ultraviolet rays hit the molecules in a comet's coma, they strip away electrons, creating ions. These ions emit their own ultraviolet light at specific wavelengths. UVS measures those wavelengths to determine what atoms and molecules are present and how much energy they're absorbing from the sun. UVS is particularly useful for studying the plasma tail, the ionized gas tail that points directly away from the sun. By measuring the ultraviolet emissions, scientists can calculate the density of ions in the tail, how fast they're moving, and how they interact with the solar wind. This provides insight into the comet's activity level. A bright ultraviolet signature means lots of ionization, which means lots of material being released from the nucleus. A weaker signature means less activity. UVS will tell us how active 3I Atlas was during the November observation. Now we come to SWE, the radio wave instrument. This one is a bit different from the others because it's not looking at light emitted or reflected by the comet itself. Instead, it's studying the environment around the comet by detecting radio waves. These waves can reveal information about magnetic fields, plasma densities, and particle interactions that aren't visible in optical or infrared light. When the solar wind encounters a comet, complex interactions occur. The charged particles in the solar wind collide with ions from the comet's coma, creating shock waves and disturbances in the surrounding space. Magis can detect these disturbances and map them in 3 dimensions. This provides a view of how the comet interacts with its environment, how the solar wind shapes the plasma tail, and whether there are any unexpected phenomena occurring in the space around the comet. Finally, there's PEP, the particle detector. This instrument directly measures charged particles, electrons, protons, and heavier ions. As the solar wind interacts with the comet, some particles are accelerated to high energies, some are deflected, some are absorbed. PEP measures the energy, direction, and type of particles in the vicinity of the comet, providing ground truth data that complements the remote sensing observations from the other instruments. PEP is particularly valuable because it measures things that can't be observed from a distance. You can look at a comet with a camera and see its structure. You can use a spectrometer to identify its composition. But to truly understand the particle dynamics in the space around the comet, you need a detector that's actually there, sampling the environment directly. And that's what PEP does. So when ESA says they deployed 5 instruments to observe 3I Atlas, they're not exaggerating. They're describing a multi-layered investigation that captured visible light, infrared radiation, ultraviolet emissions, radio waves, and direct particle measurements. Each instrument provides a different perspective on the same object. And when you combine all of that data, you get a comprehensive picture that no single instrument could provide alone. But here's what strikes me about this. Deploying all 5 instruments requires resources. It requires power from the spacecraft's solar panels or batteries. It requires data storage to hold all the measurements. It requires operational time, diverting attention from the spacecraft's primary mission. For ESA to commit those resources, they had to believe the observation was worth it. They had to believe that what they might learn about 3I Atlas justified the cost. And that tells us something important. It tells us that scientists at ESA, the people who understand this mission better than anyone, considered 3I Atlas to be a high priority target. Not just interesting, not just worth a quick photo, but important enough to dedicate significant resources to studying it. That's a strong signal. That suggests there's something about this interstellar visitor that makes it particularly valuable for scientific research. What is that something? We don't fully know yet. Maybe it's just the rarity. Interstellar comets are so uncommon that every observation is precious. You study them as thoroughly as you can because you might not get another chance. Or maybe there's something specific about 3I Atlas that caught scientists' attention. Something about its trajectory, its brightness, its behaviour that makes it stand out even among interstellar objects. Unfortunately, we won't know until the data is released. We won't know what those 5 instruments detected until February 2026. We can speculate. We can make educated guesses based on the navigation camera image and what we know about cometary physics. But the full picture remains hidden, stored in Juice's memory, waiting for the moment when the spacecraft can turn its Huygens antenna toward Earth and start transmitting. And that waiting period is both frustrating and exciting. Frustrating because we know the data exists. Exciting because we know it's going to reveal details about 3I Atlas that we can't possibly predict right now. When that data arrives, when scientists start analysing the spectra, the particle measurements, the high-resolution images, we're going to learn things about this interstellar visitor that no one has seen before. We're going to compare its composition to comets from our solar system. We're going to study how it interacts with the solar wind. We're going to measure its activity level and track how it changes as it moves through its orbit. But the Juice observation is just one piece of a larger puzzle, because while we're waiting for that data, other instruments are continuing to observe 3I Atlas. And when you step back and look at the full scope of the observation campaign, you start to see something remarkable. A global network of telescopes and spacecraft, all focused on a single object, all contributing their unique perspectives to our understanding of this interstellar visitor. Zoom out for a moment, stop thinking about Juice as a single spacecraft making a single observation. Instead, think about the bigger picture. Think about how many instruments, how many telescopes, how many spacecraft are currently tracking 3I Atlas as it moves through our solar system. Because when you add them all up, what you're looking at is unprecedented. Never before in the history of astronomy have we had this many advanced instruments simultaneously observing an interstellar object. And that fact alone tells us something about where we are as a species in our ability to study the universe. Juice is part of the story, but Hubble is watching too. The Hubble Space Telescope, one of the most famous scientific instruments ever built, has been tracking 3I Atlas for months. Hubble's observations provide a different perspective than Juice's. Hubble is closer to Earth, which means it has a different viewing angle. It can observe the comet for longer periods because it's in low Earth orbit, circling our planet every 90 minutes, and Hubble's instruments are optimized for deep space observations, capturing light from objects billions of light years away. A comet in our own solar system is right in its wheelhouse. Then there's Psyche, NASA's spacecraft currently on its way to study a metal-rich asteroid. Psyche wasn't designed to observe comets, but like Juice, it happened to be in a position where 3I Atlas was visible, and mission planners decided to take advantage of that opportunity. Psyche captured its own images of the comet, adding yet another perspective to the growing dataset. And it's not just spacecraft. Ground-based observatories around the world are tracking 3I Atlas. Professional telescopes in Chile, Hawaii, Arizona, and other locations are gathering spectroscopic data, tracking the comet's position, measuring its brightness. These observations happen every clear night, building a continuous record of the comet's behaviour as it moves through space. And amateur astronomers are contributing too. People with backyard telescopes are capturing images and sharing them online, adding to the collective knowledge base. What you're looking at is a coordinated observation campaign involving dozens of institutions, hundreds of scientists and instruments spanning Earth orbit to deep space. Everyone is looking at the same object. Everyone is contributing data. Everyone is working toward the same goal, understanding 3I Atlas. Why this level of coordination? Because interstellar objects are rare. Because they provide a window into other star systems. Because every observation adds a piece to the puzzle, and the more pieces you have, the clearer the picture becomes. But also because modern astronomy has the capability to coordinate on this scale. We have the communication networks. We have the data sharing protocols. We have international agreements that allow scientists from different countries to work together seamlessly. This is what 21st century astronomy looks like. It's global, it's collaborative, it's comprehensive. But the scale of the observation campaign also raises a question. Is this level of attention normal for an interstellar object? When Borisov was discovered, it was certainly studied extensively. Multiple telescopes observed it. Papers were published. Data was shared. But I'm not sure it received quite this level of coordinated attention across spacecraft and observatories. Maybe it did and I'm misremembering, or maybe there's something about 3i Atlas that's generating extra interest. One possibility is simply timing. When Borisov was discovered, we didn't have as many spacecraft in position to observe it. Juice hadn't launched yet. Psyche hadn't launched yet. Webb telescope wasn't operational yet. The infrastructure we have now is more robust than it was 5 years ago, so maybe the increased attention is just a function of having more tools available. Another possibility is that scientists learned from Borisov. That was the first interstellar comet we could study in detail. Researchers identified gaps in the data, things they wished they'd measured but didn't. Now, with 3i Atlas, they have a second chance. They're not going to let this opportunity pass without gathering every piece of data they can, so they're throwing everything at it. Every telescope, every spacecraft, every instrument that has a line of sight to the comet. Or maybe there's something specific about 3i Atlas that makes it particularly interesting. Maybe its trajectory is unusual. Maybe its brightness suggests something about its size or composition. Maybe preliminary observations revealed something unexpected that prompted a more intensive follow-up campaign. Without access to the internal discussions among scientists, it's hard to know, but the level of attention is notable. What we do know is that all of these observations are providing different types of data. Hubble is capturing high-resolution images over extended periods, allowing scientists to track changes in the comet's appearance. Psyche's observations add a different viewing angle, which helps in three-dimensional reconstruction of the tail structures. Ground-based telescopes are gathering spectroscopic data that reveals the comet's composition in real time, and Juice, with its 5 instruments, captured a comprehensive snapshot during its November encounter. When all of this data is combined, analysed and compared, we're going to have the most detailed picture of an interstellar comet ever assembled. We're going to know its composition, its structure, its activity level, and how it interacts with our Sun. We're going to be able to compare it directly to comets from our own solar system and look for differences that might tell us something about the star system it came from. We're going to push the boundaries of what we understand about these cosmic wanderers. But here's the thing. Despite all of this observation, despite all of these instruments, despite the unprecedented coordination, there's still so much we don't know. We don't know where 3i Atlas came from. We can calculate its trajectory backward through space, but tracing it all the way back to a specific star system is nearly impossible over interstellar distances. We don't know how long it's been travelling. Millions of years? Billions? We don't know what it's seen, what environments it's passed through, what cosmic events it's witnessed. In a very real sense, 3i Atlas is a messenger from another part of the galaxy. It carries information encoded in its composition, its structure, its physical properties. And by studying it, we're reading that message. We're learning about places we'll never visit, star systems we can only imagine. That's the profound significance of these observations. It's not just about understanding one comet. It's about expanding our knowledge of the galaxy itself. And the network watching 3i Atlas is proof that we're capable of doing that. We're capable of coordinating observations across continents and spacecraft. We're capable of sharing data internationally. We're capable of working together to answer fundamental questions about the universe. That's not something to take for granted. That's an achievement in itself. But as much as we're learning, as much as we're observing, we're still waiting. We're still waiting for the Juice data to arrive in February 2026. We're still waiting to see what those 5 instruments revealed. We're still waiting for the full picture to emerge. And in the meantime, 3i Atlas continues its journey, getting closer to the Sun, getting brighter, getting more active. The story isn't over. It's still unfolding, and the coming weeks will bring us closer to understanding what this interstellar visitor truly is and what it can teach us about the galaxy we call home. So let's bring this all together. Let's take a step back and look at what we actually know, what we're still waiting to discover, and what this all means for our understanding of interstellar objects as they pass through our solar system. Because despite the speculation, despite the questions, despite the month-long wait between observation and announcement, there's a clear story here. It's a story about scientific opportunity, technological capability, and the enduring human drive to understand things that come from beyond our world. Here's what we know for certain. On November 4th, ESA's Juice spacecraft made its closest approach to 3I Atlas, an interstellar comet making its way through our solar system. During this encounter, Juice deployed 5 scientific instruments to study the comet across multiple wavelengths and measurement types. One of those instruments, the navigation camera, captured an image showing 3I Atlas with 2 distinct tails, one likely made of ionized gas, the other made of dust particles. This image was released to the public on December 4th, a month after the observation took place. The full science data from the other instruments won't be transmitted to Earth until February 2026 due to the spacecraft's current orientation and antenna configuration. That's the factual baseline. Everything else is interpretation, speculation, or questions waiting to be answered, and that's okay. That's how science works. You gather data, you form hypotheses. You wait for more data to confirm or refute those hypotheses. The process takes time. It requires patience. It doesn't always satisfy our desire for immediate answers. But within that factual baseline, there are things worth emphasizing. The dual-tail structure visible in the navigation camera image tells us 3I Atlas is actively outgassing, producing enough material to form distinct tail features visible from millions of miles away. The decision to deploy 5 instruments tells us ESA considered this observation scientifically valuable enough to justify diverting resources from Juice's primary mission. The coordination with other observatories tells us the scientific community recognizes 3I Atlas as an important research target, and the delay in releasing the full science data, while frustrating, is consistent with standard spacecraft operations and doesn't suggest any deliberate withholding of information. Now, what are we waiting for? We're waiting for the Juice data to arrive in February 2026. We're waiting to see what Janus, Magis, UVS, SW, and PEP detected during the November observation. We're waiting for detailed composition analysis, particle measurements, and high-resolution images that will reveal aspects of 3I Atlas we can't see in the navigation camera photo. That data will be transformative. It will provide the most comprehensive view of an interstellar comet we've ever had. It will allow direct comparisons with comets from our own solar system. It will tell us whether interstellar material is fundamentally different or surprisingly similar to what we find around our Sun. But we're not just waiting for February 2026, we're also watching what happens in the coming weeks. 3I Atlas is approaching its closest point to the Sun later this month. As it gets closer, solar heating will intensify. The comet will become more active, the tails will grow longer and brighter, and all of those ground-based telescopes, all of those spacecraft with line of sight to the comet, will be watching, gathering data in real time. So while we're waiting for the Juice data from November, we're simultaneously getting new observations of how the comet is changing as it moves through its orbit. This creates a dynamic situation where our understanding is constantly evolving. Every new observation adds detail, every new data set provides context, and by the time the Juice data arrives, we'll already know so much more about 3I Atlas than we did in November. The Juice observation will be one snapshot in a much larger timeline of observations spanning months and involving dozens of instruments. What does this all mean for the bigger picture of interstellar object research? It means we're getting better at this. We're learning how to identify these objects quickly, track them effectively, and coordinate observations across international boundaries. When Oumuamua was discovered, we were caught off guard. We didn't realize what it was until it was too late to study it properly. With Borisov, we did better. We had time to plan observations, deploy instruments, and gather meaningful data. Now with 3I Atlas, we're doing even better. We have spacecraft in position. We have protocols in place. We have the infrastructure to study these objects comprehensively, and that bodes well for the future, because 3I Atlas won't be the last interstellar object to visit our solar system. Statistical models suggest that several of these objects pass through every year, though most of them are too faint or too far away to detect. As our telescopes get better, as our detection algorithms improve, we'll start spotting more of them. And when we do, we'll have the experience and infrastructure to study them immediately. Maybe in the not-too-distant future, we'll even send a dedicated mission to intercept an interstellar object. Imagine a spacecraft designed specifically to rendezvous with these visitors, equipped with instruments optimized for close-range study, capable of extended observation over weeks or months. That's the next frontier. That's where this field is heading, and observations like the one Juice conducted in November are laying the groundwork for that future. But let's come back to the present. Let's come back to that image of Three-Eye Atlas with its two tails stretching across the darkness of space. That image is more than just a pretty picture. It's evidence of a comet actively interacting with our Sun. It's proof that interstellar objects behave in ways we can observe and measure. It's confirmation that our spacecraft, our instruments, and our scientific methods are capable of extracting meaningful information from these rare cosmic visitors. And it's a reminder that there's still so much we don't know, so many questions left unanswered, so many mysteries waiting to be explored. I started this video by telling you about an image that shouldn't exist. A comet with two tails captured by a spacecraft that wasn't supposed to be looking at it. And I hope by now you understand why that image matters. Not because it defies explanation, but because it invites investigation. Not because it suggests something sinister or hidden, but because it represents a scientific opportunity that's being pursued with remarkable thoroughness and coordination. Not because it answers all our questions, but because it raises new ones, better ones, questions that will drive research for years to come. The story of Three-Eye Atlas is still being written. The observations are ongoing, the data is accumulating, and in February 2026, when that Juice science data finally arrives, we're going to see a new chapter unfold. We're going to learn things about this interstellar visitor that we can't predict right now. And those discoveries will inform future observations, future missions, future investigations into the nature of objects from beyond our solar system. So here's what I want you to take away from this. First, stay curious. Keep asking questions. Keep looking for information, but also be patient. Science takes time. Data processing takes time. Analysis takes time. The delay between observation and revelation isn't a cover-up. It's just the reality of how careful, thorough research works. Second, pay attention to what happens later this month as Three-Eye Atlas makes its closest approach to the Sun. Watch for new images, new data, new insights from the observatories tracking this comet. The story is evolving in real time and you're witnessing it as it unfolds. Third, appreciate the scale of what's happening. A global network of instruments working together to study something that came from another star system. That's not normal. That's extraordinary. That's a testament to how far we've come as a species in our ability to study the universe. And finally, share this information. Talk about it with friends who are interested in space. Post about it. Spread the word. Because the more people who know about Three-Eye Atlas, the more people who understand what's being observed and why it matters, the stronger the support for future missions, future telescopes, future investments in understanding our place in the galaxy. This is our story. This is humanity reaching out to touch something that doesn't belong to our Sun, and it's worth celebrating. If you made it this far, thank you for sticking with me through this investigation. Drop a comment and let me know what you think. Are you as fascinated by this as I am? What questions do you still have, and where are you watching from? I want to know how global this community really is. Hit that subscribe button if you haven't already, because when that Juice data arrives in February 2026, I'll be here breaking it down, analysing what it means, and exploring the new mysteries it reveals. Until then, keep looking up, keep asking questions, and remember that somewhere out there, an interstellar visitor is racing through our solar system, carrying secrets from another corner of the galaxy. We're lucky to be alive at a time when we can actually study it.